Hello calculus folks, here we are with our third video, which deals with the sliding ladder. This is a classic problem, and remember the steps that we want to go through. I'm just going to outline them again one more time real quick. We want to first draw and label a diagram. After we read and understand the problem, we want to find the static equation. We want to try to simplify the equation to one variable if possible, and we want to take a time-based derivative and then solve for the rate. So we have a whole bunch of steps that we want to get through for this problem. This is a classic problem. Typically, whenever we're learning related rates, we always have the ladder problem. It's a fun one to teach in class, and we always try to make it interesting, saying that the teacher is on the ladder and one of the students is going to kick the ladder out from under them, and it just conjures up all great images, for a moving or a related rates problem. So we're going to get started where we're going to first draw our picture, and we have the house, and then we have the ladder that's out away from the house. And the ladder, it has a well, let's read the problem, understand what they're asking. So I'm going to highlight it as I read it. A 26-foot ladder is leaning on a house. The foot of the ladder is 10 feet from the base of the house, and if the bottom of the ladder is given a kick by some student or maybe someone else on the faculty at the school at 5 inches per second, what initial velocity will the top of the ladder experience, and in what direction? So quite a bit of information there, and we want to try to draw a diagram to capture all the information that the problem is given. So what I'd like you to do is re-examine this problem while I pause the video, and then when I unpause the video and when you come back, I'm going to have the diagram all drawn up as far as what information goes where. And let's compare diagrams and see if we match. Okay, class, so here we have the diagram, and I haven't labeled it because half the fun of this problem is labeling the diagram. So we have a picture. I'm on the top of the ladder, and the ladder gets kicked out at a rate of, we'll call this the x dt. That's going to be the x velocity, and that is given a value of 5 inches per second. The ladder is moving down at a rate which we don't know yet, but we'd like to calculate, and that would be dy dt. The triangle has an initial setup, so I'm going to label that in blue, and the triangle, the hypotenuse of the ladder, or the ladder, has a length of 26 feet, and the the initial distance from the house is 10 feet. So what we need to do is come up with an equation that relates all the parameters to one static equation, and that's what part 2 says, is to find a static equation. So I'm just going to label these as z, y, and x. And some of the earlier videos had shown that if we have a setup with a right triangle with the 3 sides, our go-to equation is the Pythagorean relationship, Pythagorean theorem. What I'd like you to do in the next step is I'd like you to take a time-based derivative of this equation, and then make sure we compare answers and we match up with what the Pythagorean with what the time-based derivative would be. So I'm going to pause the video, and I'd like you to work on that with your groups. Okay, well, we're back, and I just took the time-based derivative, and I had the derivative of x squared is 2x dx dt. The derivative of y squared with respect to time is 2y dy dt, and the derivative of z squared is 2z dz dt. The 2's can all cancel out. Maybe you've done that already, and we basically have a nice equation: x times dx dt plus y times dy dt equals z times dz dt. So now we need to figure out what x, y, and z are, because x, y, and z, we're only given z is to be 26, x is 10, so we need to calculate what y would be. So before we can use this equation, we need to find what the value of y is. And so I'd like you to work on that with your group, and I'm going to pause the video so I can work on it, and when we come back together, hopefully we have the same answer. Okay, well, if you use the Pythagorean theorem, you find that the missing third side for y is 24, and wasn't that nice that this was a Pythagorean triplet? If you didn't notice, you didn't have to use Pythagorean theorem. This you could have thought of as similar triangles. You have a 5, 13, and this side would be 12 if it was reduced by a factor of 2. So that makes our third side 24. If you did do Pythagorean theorem, these are the steps that got you to y equals 24. Now, you have all of the sides of the triangle, and we have the rates of the triangle. So let's go through and fill in the blanks of what we know and try to understand what we have to find in the equation still. So the x value is equal to 10. I'm going to consider 10 to be measured from the origin, 0, 0. So that value of 10, I'm going to consider that to be in the positive direction, and I'll consider down to be in the negative direction. So we're going to measure this. We have positive 10. The x dt is moving away from the origin, so that's also positive. So we'll say that's 5 inches per second. And then we have, I have a unit mismatch here. So let me change this 10 to 120 inches. Because I want to be consistent with my units. 10 feet is 120 inches. So then I have my y value is 24 feet. So that would be, I have to calculate that. So let me calculate that. That's going to be 24 feet times 12. That's 288 inches. And the y dt is unknown, so I've got to find that. And then we have the z value, which is 26 feet, so 26 times 12 is equal to 312 inches. And I have the z dt. So we have almost all of the blanks filled in, but we have two variables we don't know. We have dy dt and dz dt. What I'd like you guys to talk about is what should we do with dy dt or dz dt. We're trying to solve for dy dt, but there's something that you should know about the zdt from the makeup of the problem. So discuss it with each other for a couple minutes, and then after you come up with your ideas on how to find dz dt, and dy dt, come back to the video, and hopefully our solutions coincide. Okay, well, we're back, and here's the thing. Hopefully you came to the conclusion from looking at the problem that because this is a ladder, that the z length does not change. And when the z length does not change, the z dt is equal to 0. And that simplifies things a great deal for us, because now we're able to cancel this term out completely. And now we have 600 inches squared per second, and that equals negative 288 inches times dy dt. And when we solve for this by division, we get 600 divided by 288. Now this is going to be inches squared per second over inches, which our units will work out nicely to be inches per second. And so I need to calculate 600 divided by 288. And I get 2.083 inches per second. Negative indicates that it is moving downward. So it makes reasonable sense that the object is, this is on the order of what the kickout velocity was of 5 inches per second. So now we know that dy dt is negative 2.08 inches per second. Hope this video helps, and if this video is acceptable to what you're working on, then like the video, and also, if you wouldn't mind, subscribe to the channel, and please comment and ask or suggest any other videos that we could do to help you out with this calculus process.